Okay, so studying we are studying about antenna radiation field. Okay, antenna radiation field. Okay, so now up to now we have discussed uh, the magnetic vector potential of an antenna. Okay, then using that magnetic vector potential, we have found the H field and E field, magnetic field and electric field. Okay, so using magnetic field and electric field, we found another important parameter of an antenna, that is average power density. Okay, okay. Then using average power density, we have found the total radiated power of the antenna. Okay, so up to now we have discussed these parameters of the antenna, of an antenna. Okay, uh, okay, okay, and we have to discuss uh, some other important parameters also. Okay, before that, okay, before starting our discussion, I want to uh, introduce you a new, maybe these terms may be new for you. Okay, that is solid angle. Okay, solid angle. Okay, so you know that normally we know what is angle, no? We know what is angle. Okay, so normally we are dealing with two-dimension angles, no? Okay, up to now. Okay, we have dealt with two-dimension angle. Okay, two-dimension angle. Okay, so we can use radians or degree. Okay, radians or degree to measure a two-dimension angle, no? Okay, for example, if you consider an angle like this, okay, this kind of angle, okay, so this is angle, so you know that this is a two-dimension, no? Okay, so you can measure this angle using radians or degree. Okay, radians or degree. Okay, so maybe I think you know the definition of the radians. Okay, I think you know the definition of the radians. Okay, so we define the radians like this. Okay, so if you consider a circle, okay, and okay, and if you consider a section on this circle, okay, so let's say that this is the length of this section, okay, measured in meter or centimeter or millimeter or something, okay, is L, okay, and this is the radius of the circle, okay. So this angle, okay, this angle theta, okay, theta radians, okay, if you measure the theta in radians, that is equal to nothing but this length divided by the radius of the circle. Okay, so this is the definition of the radians. No, maybe not the definition. Okay, it is an explanation for the radians. Okay, this is how we explain the radian. Okay, so now consider a sphere. Okay, consider a sphere. Okay, so you know that sphere is a three-dimensional object. Okay, so I can't draw it here. Okay, so it is like this. No, it is a sphere. Okay, a ball. Okay, so if you consider a sphere, Okay. And if you take, okay, if you take a here in circle, you are taking a length. Okay, it is a section. Okay, section of the length. It is a section of the circle. That is a length. Okay, so if you consider section of a sphere, okay, sphere, it is area. Okay, it is area. Okay, so if you select a area in the in this sphere, okay, in this sphere, okay, and so this is the, so this is just like a cone, no, this is just like a cone. Okay, so this is the radius and this is the area of a of the sphere. Okay, so it is like this. Okay, so you have selected this kind of section, no? Okay, so actually this angle we called as solid angle. Okay, so this angle we normally referred as solid angle. So you can say that, you can see that it is a three-dimensional angle. It is just like a coin. Here it is just a two-dimension. Okay, but here it is a cone. Okay, so this angle surrounded by this cone is called the solid angle. Okay, so so this is the solid angle. Okay, so it is normally mentioned like this, omega. Okay, so the omega is defined as, okay, so this is measured in, so you know that two-dimension angles are measuring using the radians. Okay, and this solid angle we are measuring using that is called uh, star radians. Star radians, yeah, radians or something. I can't pronounce it. Okay, radians maybe. Okay, so this is the star radians is the unit to measure the solid angle, and it is defined as, okay, so here it is length divided by r. So here you have select a area, so it is a area divided by the square of this radius, r square. So this is how we define the solid angle or star radians. Okay, star radians or star radians. Okay. Okay. Now, so I think you got the idea. Okay, so if you have any problem, please ask me. Okay, then I can explain you. So if you consider a XYZ coordinate again, okay, okay. So let's say that you have this kind of surface. Okay, so you have this kind of surface. Okay, you have a surface like this. Okay, you have a surface like this. Okay, and if you consider the unit vector perpendicular to this surface, let's say that it is n hat. Okay, so normally we refer this n hat to indicate the wave propagation direction. No, I think you can remember it. Okay, and okay, so let's say that this is uh, very small area. Okay, very small area, ds. Okay, so this is very small area. Okay, and if you connect this one, okay, so you know that this is a, if you consider this position, okay, Okay, so this you can consider that this area is very small, so it is just like a point. Okay, so if you consider this point, okay, so it is a position. Okay, so that that position vector direction is r hat. Okay, r hat. Okay, so let's say that the angle between this n hat and r hat is alpha. Okay, so now you want to find the solid angle due to this surface. Okay, so this surface is like this. Okay, so you can see that here the area is perpendicular to r hat. No, the perpendicular to r hat. So this is the r. Okay, so if you consider very small portion on the sphere, okay, so that is perpendicular to r hat. Okay, r hat, and it is should be divided by r square. Okay, now to find the steradians of this angle. Okay, this angle, this surface should be perpendicular to r hat. Okay, so that is the definition. Okay, this surface should be perpendicular to r hat. Okay, so if you consider that this is alpha. Okay, and if you consider this is this surface. Okay, this is the surface. Okay, this is the surface. Okay, and you know that, so I have told you that n hat is perpendicular to the surface. Okay, not r hat. R hat is not perpendicular to the uh, surface. But if you want to find the steradian value, this d omega, okay, the solid angle, you have to find the area perpendicular to this r hat. Okay, so that is the definition. Okay, so here the area is perpendicular to r hat, but this area is not perpendicular to r hat, so we have to get the perpendicular component to the r hat. Okay, so you know that this is so this is the space, and this is n hat, that is perpendicular to r hat. Okay? So this is 90. Okay, and if you consider the line perpendicular this r hat, okay, like this. Okay, so it is maybe like this, no? So that is perpendicular to r hat. Okay, so this angle is 90 and this angle is alpha, so this angle will be 90 minus alpha. So this line is perpendicular to r hat. Okay, so it is 90 minus alpha, this angle. Okay, and so this one and this one also 90. Okay, so this angle also will be 90 minus alpha, and this one. Okay, so you can see that this one and this one also, this is the line perpendicular to r hat. Okay, so this one and this one, that means this angle also will be 90. Okay, so what is the angle? This angle, that is alpha. Okay, so if you consider, so this is your surface. Okay, so I will write it here if you are not here it. Okay, so this is the position you are going to measure. Okay, and this is the r hat. Okay, and this is the alpha. Okay, so this is n hat. Okay, the, the vector, unit vector, the direction perpendicular to this surface. Okay, and if you get a line perpendicular to this one. Okay, so this is perpendicular to this one. Okay, and this is the surface of the the surface of the angle, surface of the, sorry, line, this is the surface direction. Okay, and this will be alpha. Okay, so this will be 90 minus alpha, and this will be again alpha. Okay, so if you consider ds, this is the area, ds cos theta, ds cos alpha. If you consider ds cos alpha, that is the component perpendicular to this r hat. Okay, so if you consider this one, if you get this direction, that is ds cos alpha. Okay, so that is perpendicular to the r hat. Okay, so d omega, you can say that d omega is equal to ds cos alpha divided by r square. Okay, and what is this cos alpha? Okay, so you know that cos alpha. So this is the alpha, no? So this is n hat and r hat is a unit vector. Okay, so if you take the dot product, n hat and r hat, n hat dot r hat, what is the answer? That is n hat magnitude, r hat magnitude, cos alpha. No, so n hat magnitude and r hat magnitude is 1 because it is those are unit vectors. So n hat dot r hat is cos alpha. Okay, so cos alpha is equal to dot product of n hat and r hat. Okay, so we can replace this cos alpha with the dot product of n hat and r hat. Okay, so this also you need to maybe used. Okay, and okay, now uh, if you consider if you consider, so you have a sphere like this. Okay, so you have a sphere, this is sphere. Okay, so if you consider area here like this. Okay, and so this is very small area ds. Okay, and this is the radians, star radians value, d omega angle. Okay, so d omega is the angle uh, formed by this small area. Okay, so if you want it clear. Okay, okay, now consider this one. Okay, so if you have a sphere. Okay, so if you have a sphere like this. Okay, and if you consider a small area on this sphere surface. Okay, so there is a solid angle created by this area, no? Like this. Okay, so this area, so this is very small area. Okay, so let's say that that is ds, and that small area created a small angle d omega. Okay, solid angle d omega. Okay, now you want to find the total angle of this sphere, solid angle, total solid angle of this sphere. Okay, so you need to find the total angle. Let's say that omega. Okay, so it is equal to, you have d omega. Okay, and you have to add all d omega all over the sphere. No? Okay, so it is defined. Okay, it is formed from the surface. Okay, so you have to, if you are doing the surface integral, okay, throughout this sphere, okay, for the d omega, you will get the solid angle of a sphere. So this is the omega, this is the solid angle of the sphere you can get. Okay, so you have to do a surface integral. Okay, so you know that you need to do double integral. Okay, surface integral. Okay, so to do the surface integral, okay, So you can use this identity. Okay, you can use this identity. D omega is equal to Vs n hat r hat r square. Okay, so you can use that. Okay, so you can use s hat ds n hat r hat divided by r square. Okay, so you are going to, so here you have a small area ds, and you are going to do the integral for the whole surface. Okay, so we have found that previously ds equal to, if this is r, okay, and if this is r, okay, and this is theta, okay, if this is r and theta, we have found that r d theta r sine theta d phi. Okay, so ds is equal to this one. We have found this. We have used this in previous week. Okay, so you can use that one. Okay, now you can see that you have variable d theta and d phi. Okay, so you have to integrate. You have to do the double integral. Okay, uh, through d theta and d phi. Okay, so theta is from 0 to theta is this angle. Okay, theta is this angle and phi is this angle, vertical angle, horizontal angle. The theta is the vertical angle. Okay, so um, you have to integrate 5 from 0 to 2 5. Okay, so this is 5. Okay, and theta from 0 to 5. Okay, so you have to integrate all the area. Okay, 0 to 2 5 and 0 to 5, then all area is covered. Okay, and so you can uh, apply this identity to here. Okay, so here you have r square, the r square sine theta d theta d5 divided by r square. Okay, and n hat and r hat is also there. No, n hat and r hat is also there. Okay, n hat and r hat is also there. Okay, now you see me. Okay, so now you see that we have selected the perpendicular area. No, okay, so this is the r hat direction. Okay, and the perpendicular direction is the n hat. Okay, so in this case n hat and r hat is equal. No, okay, here for this one, n hat and r hat has alpha separation. Okay, but in this case, okay, because the r hat is also perpendicular to the surface, selected surface. Okay, so in this case n hat and r hat is identical. Okay, so here actually this is r hat. No, the n hat can be replaced by r hat. Okay, so what is the r hat dot r hat? Okay, so that is magnitude of r hat, then the magnitude of r hat cos the angle between r hat and r hat. Okay, so the angle is 0. No, here 0. So what is cos 0? That is 1. Okay, so if you get a cross product of a same unit vector, you will have always 1. Okay, so this is, so you can cancel this and you have 1 here. Okay, and this r square and r square cancel out. Okay, then you have to do this integral. Omega is equal to 0 to 2 5, 0 to 5. Okay, sine theta d theta d5. Okay, so d5. Okay, so if you consider d5, if you integrate it with d5, it is very simple because no 5 terms are here. Okay, so 0 to 2 5, you have to integrate d5. Okay, so you will get the answer 2 5. Okay, and you have to then multiply, you have to then evaluate 0 to 5 sine theta d theta, this value, okay? So what is this? Sine theta is nothing but minus cos theta from 0 to 5, okay? So what is the answer here? Minus cos 5 minus cos 5 plus minus cos 5 plus cos 0, okay? So what is minus cos 5, okay? So you know that the cos wave is like this, no? Okay, and this is 5 by 2 and this is 5, and this is 5 by 2 and this is 5, okay? So minus cos 5 is this one, that is equal to minus 1, okay? So minus cos 5 is equal to minus 1, so minus minus you will have plus 1, okay? Plus cos 0, here plus cos 0, no? Plus 0 is 1, okay? So plus 1, and you have 2, okay? So what is the omega value? You have 2, 5, 4, 5, okay? So this is the star radiance. Star radiance, okay? Star radiance, okay? So this is the solid angle of the sphere, okay? Okay. So I think maybe this knowledge also may be needed for you. Solid angle of the sphere, okay? So now we will move to our parameters, okay? Now, we have what is called, we have to find what is called radiation intensity. Radiation intensity. Okay, so this is also very important parameter. It is normally referred as U. Okay, so radiation intensity is defined as power radiated by an antenna, okay, per unit solid angle. Solid angle. Okay, so this is the power radiated by an antenna per solid unit angle. Okay, uh, the power radiated through a unit solid angle. Okay, so that is called the radiation intensity. Okay, so very easily we can find this. Okay, so we know that average power density is average. What is average power density? Can you remember? That is the power. Okay, this is the power radiated across a unit area. This is the power radiated across the unit area. This is the definition of the average power density. Okay. Now we have to find the power radiated. Okay. Now we need to find power radiated across a unit solid angle, not the area, solid angle. Okay. So you know that if you consider a sphere, okay, if you consider a sphere, if you consider, okay, so this is the definition of star radiance, no? If you get a area, okay, the solid angle related to this a area is nothing but a divided by r square. Okay, so this is the definition. Can you remember? This is the definition of the solid angle. Okay, so it is, we have defined it like this, no? This one, okay? So this is the definition, okay? So if you consider a area of a sphere, okay? Sphere, A divided by R square is the solid angle, okay? Corresponding to this A area. Okay, so this is the area and this is the unit solid angle. Solid angle. Okay, so if you consider one area, if you connect, if you selected the unity area, that means this area should be divided by a. Okay, then what is the solid angle corresponding to unit area? That is 1 square. 1 by r square. No? So this also, this side also should be divided by a. Then a cancel out and you will get 1 divided by r square. Okay, so what is this? This is the solid angle corresponding to unit area. Unit area. Okay. Now, okay. Now you know that for unit area, the corresponding power is nothing but S average. The average power density. This is the power across the unit area. Okay. For unit area, you have this power. Okay. So this power this power, the average power density, you will you had the vector, no? Okay. So if you are finding it for unit angle, okay, the magnitude, we are interested in the magnitude only. Okay. So the magnitude of, or the value of the average power density per unit angle is the magnitude of SAVG. No? So if you get the magnitude of the power density, average power density, that is the power radiated through unit angle. Okay, so this is the power radiated through a unit angle, unit area, sorry, unit area. Okay, and unit area is corresponding to 1 by r square star radians. Okay, so this is the power corresponding to 1 divided by r square star radians, the solid angles. No, so this is the power related with this solid angle. Okay, S average. Okay, so what is the power related with one solid angle? That is nothing but you have to divide this by 1 by r square. Okay, in the same manner, you have to divide this side also, this SAVG magnitude also by 1 by r square. Okay, so you will get r square SAVG magnitude. Okay, so what is this? This is the power radiated through a unit angle. This is the power radiated through a unit solid angle. Okay, so that is we called radiation intensity. Okay, so radiation intensity is equal to r square magnitude of SAVG. Okay, so this is the radiation intensity. This is how we find the radiation intensity. Okay, this is how we find the radiation intensity. Okay, then if you consider infinitesimal, infinite small dipole, okay, dipole, we know that the SAVG is equal to, okay, we have found this, that is equal to N K, sorry, R square meter, this is meter, maybe not, K square, the magnitude of I square, L square, sine square theta. Okay, sine square theta divided by 32 5 square r square. Okay, the r is not here. Okay, so r is not here. N theta k square I magnitude I square L square sine square theta 32 5 square r square. Okay, so the r is the distance and L is the length of the dipole. Okay, and it is a vector and you have the direction r hat. Okay, so this is the direction. Okay, so if you get the magnitude, you have to you have to you have to ignore this direction. Okay, and if you get the magnitude, SAVG magnitude. Okay, so here you don't have any complex component. Huh? Okay, so this is a total real components because I also you get the magnitude value. Okay, so here all are real values are there. So this will be a real value. Okay, not a complex value. Okay, so the magnitude of S average will be meter k square I square L square sine square theta divided by 32 5 square r square. Okay, and if you want to find the U, okay, radiation intensity, you have to multiply this by r square. And here also should be multiplied by r square because U is equal to r square is AEG. Then r square cancel out. Okay. And this is the radiation intensity for infinite small dipole. Okay. So for infinite small dipole, the radiation intensity is square L square sin square T divided by 32 5 square. Okay. So this is the radiation intensity for a uh, infinite small dipole. Okay. So you can see that this radiation is not uniform. The radiation intensity is not uniform. Okay, because it is changing with this theta. Okay, so if you consider, if you place this antenna like this, okay, so theta is the vertical angle, this angle. Okay, theta is the vertical angle, this angle, this is the theta. Okay, and phi is the horizontal angle like this. Okay, so phi we normally referred as azimuth actually. Theta is the tilt. Okay, okay, you no need to remember this word. Okay, okay, so you can see that it is not depending on the phi. Okay, so if you consider any phi value around this, you have a uniform intensity. Okay, but this side it is not uniform, it is changing. Okay, in this direction it is changed. Okay, so u is not a uniform value. Okay, it will be changed. Okay, it will be changed. Okay, now if I ask you to find what is the maximum radiation intensity, radiation intensity, try to find the answer for this by yourself first. Pause the video and try to answer answer the try to find the answer for this question. Okay, so it is very easy, you can find it. Okay, anyway, I will explain it how to find. Okay, so you can see that this u is changing due to sine square. Okay, so if you get the sine square maximum, okay, if you get this value maximum, you will get the maximum intensity. Okay, so what is the maximum of sine square theta? Okay, so maximum is when the theta is equal to 0. No? Okay, so at that time sine theta is equal to 1. Okay, so sine square theta also equal to 1. Okay, so this is the maximum value. Okay, so here the u maximum value is n k square I square L square. Now sine square theta is equal to 1, 32, 5 square. Okay, so this is the maximum radiation intensity. Okay, and you can see that this u, this u can be also defined as u max. Yeah, actually, so I think you know that. Okay, so, sorry, this is not like this. Okay, okay, so I think you can now you can understand what is the u radiation intensity and what is the maximum radiation intensity. Okay, because the radiation intensity is not uniform. Okay, so there can be a maximum radiation intensity. Okay, uh, and you have the maximum radiation also. Okay, and if you divide the radiation intensity by the maximum intensity, you will get what is called nominalized radiation intensity. Okay, so this is nominalized radiation intensity. Nominalized radiation intensity. Okay, radiation intensity. Okay, and this is the radiation intensity, and this is U max. Okay, so in other words, you can write the radiation intensity is equal to uh, nominalized radiation intensity times maximum radiation intensity. Okay, this way also you can define this. Okay, and this UN is important. Normalized radiation intensity is important. To draw the intensity pattern of antenna, we normally use this normalized radiation. Okay, so if you find the normalized radiation of the infinite small antenna, okay, UN normalized intensity of the infinite small antenna, okay, antenna. So what is the value? Okay, so you know that UN is nothing but U divided by U max. Okay, so what is the U? This is the U and this is the U max. Okay, so if you divided U by U max, this part and this part cancel out and you will get only sine square theta. Okay, so you will have only sine square theta. Okay, so this is the nominalized pattern value, and this we normally use this, nominalized intensity, radiation intensity, to draw or to estimate the radiation pattern of an antenna. Okay, radiation pattern of an antenna. Okay, so if you want to find the radiation pattern of the antenna, okay, so you can see that it is related with the T, okay, theta, okay. So if this is the Z axis and this is the Y axis, okay, so you can see that the radiation intensity change in this direction, in the tilt direction, not in the phi, okay, phi direction. This direction, it is not changed, okay. So you can find, you can draw the radiation intensity, okay. So you can see that the minimum radiation intensity is when the theta is equal to 0. Sorry, theta is equal to 5, okay. When the theta is equal to 5, you will get the minimum radiation intensity, okay. So when the theta is 5, okay, theta is 5, you will get the minimum radiation intensity, that is 0, okay. Then when you are increasing the theta like this, okay, so this is, so we are measuring theta in this direction, okay, we are measuring theta in this direction, okay. So this is the theta direction now, okay. Yeah, theta is measuring in this direction, okay. So when theta is zero, you will get maximum value, and theta is 90. Sorry, sine theta is like this, no? Sine theta is like this, no? Sorry, sine theta is like this, okay? So actually you will get the maximum at the 90, no? You will get the maximum at the 90, okay? So at the zero, you will get zero, okay? So sine theta is measuring in this direction, okay? So when the theta is zero, it is equal to zero, okay, it is equal to zero. Now theta is increasing, okay, theta is increasing, and your intensity was increasing in like this, okay, like this one also increasing like this, okay. And when the theta is equal to 90, okay, that means this point, the theta is 90, you will get the maximum value, that is 1, like this, okay. And again uh, theta is going to other direction like this, okay, up to 90, okay. Then you will get again the intensity is changing like this, okay. So intensity is changing like this up to, sorry, this is theta, sorry, this is theta 90. So here the theta is 0, here the theta is 90, and this is 90 to 180, okay, not this side, 90 to 180, that means here 90 to 5. This is 5 by 2 to 5, okay. Again, theta is decreasing like this. Okay. Theta is decreasing like this, okay. So you will get this kind of radiation pattern, okay. And this is not depending on the theta, okay. Only depending on the theta, not the phi, okay. So these are normally symmetrical antenna, okay. So you will get a intensity pattern in this direction also, like this, okay. So this way you can draw the radiation pattern for a antenna using the nominalize radiation intensity, okay, like this, okay. And so you can see that this antenna is not directing uniformly, no, it is directing ununiformly, okay. And this side you will get the maximum intensity, okay. This side you will get the maximum intensity, okay. So this is, okay, actually this direction, okay. So antenna is placed like this, no, antenna is placed like this, okay. So this is the direction perpendicular to antenna, okay. And this direction we normally referred as broadside direction, broadside direction, okay, broadside direction, okay. And this the direction parallel to the antenna, this direction we normally referred as end fire direction, end fire direction, okay. So you have broadside direction and end fire direction, okay. And you can see that this infinitesimal antenna is radiating in broadside direction, okay. The maximum intensity is in broadside direction, okay. In this direction you have the maximum intensity, that is in broadside direction, okay. So this is called broadside antenna, okay, because the maximum intensity is broadside direction. So these are called broadside antenna, okay. Okay. So, so you can see that this is not a uniform antenna, no? Actually, there are some uniform antennas, okay? Actually, there is no uniform antenna in all direction and tilt and azimuth, okay? So if you consider, it is actually a hypothetical antenna, okay? So, uh, so if we imagine this antenna is distribution uniformly all over the space, okay? Uniformly all over the space, okay? That is for 5 steradians angle, steradians angle. If it is uniformly throughout all the for 5 steradians angle, we called it as isotropic antenna. Isotropic antenna. Okay, isotropic antenna. Okay, but practically we don't have a isotropic antenna. Okay, there are some antenna called omni antenna. Okay, that omni antenna is so normally you can see that maybe you know that for a indoor coverage we are using omni antenna. Okay, so maybe you can see that the antenna mounted on the civilian. Okay, so that is to give you the signal from the base station. Okay, maybe from Dialog Mobitel base station. This base station is connected to this antenna. Okay, and so these are omni antennas. It is uniformly distribution in this direction. Okay, in 5 direction. Okay, that is why it is called omni antenna. But actually, it is not directly in this direction. Okay, this direction it is not radiating uniformly. Okay, so omni antenna is also not the isotropic antenna. Okay. Uh, okay, so that is the uh, thing you should understand here. Okay, and another thing is okay, and also we have defined another parameters called u naught. Okay, so that is actually defined as um, the if you have a it is how it is defined like this. Okay, the u naught is okay, u naught is, so you see that this antenna infinitesimal antenna is not propagating, not radiating uniformly. Okay, it is not propagating uniformly. Let's say that it is uniformly propagated. Okay, uniformly propagated. Okay, and if it is uniformly propagated and if it radiate in the same total power, okay, so that is defined as u naught. Okay, so we can we can say it is like this, radiation intensity, radiation intensity, okay, radiation intensity of an isotropic antenna, isotropic antenna radiating the same total power, same total power. That is defined as u naught. Okay, so 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 you can see that the u, okay, so for infinitesimal dipole, u, okay, is not uniform. Okay, u is not uniform, but there is a total radiated power. No? There's a total radiated power. Okay, so if you divide that total radiated power, okay, so you know, so I told you that isotropic antenna means it is uniformly, it is uniformly uh, it is uniformly radiating through this whole 4-5 star radian and star radian value, star radian angle. Okay, so this is the angle completely cover the sphere. Okay, so the same power, okay, if you have radiating through this 4-5 star radians angles, okay, so that is PT is divided by R5 4-5, okay, so that is equal to the U naught. Okay, so that is the radiation intensity of, if we consider this antenna is a isotropic antenna. Okay, so this is the radiation intensity. Okay, PT divided by 4-5. Okay, and this one also, I think, if you can't understand, please ask me. Okay, then I can explain this. Okay, I hope you can understand this. Okay, so try to understand by yourself. Okay, what is this? Okay, I think the enough informations are there. You can try to understand by yourself. If you can't understand by yourself, you can ask me. Okay, first you can discuss with your friend and then you can ask me if you can't find the answer. Okay, if you can't, if you still, if you couldn't understand, you can ask me. Okay, so maybe in future we also need this parameters also. This is the radiation intensity of an isotopic antenna radiating the same total power of the considered antenna. Okay, okay, so that is the U naught. Okay, um, okay, now I think that is enough. Okay, related with the radiation intensity. Okay, so we have finally you can see that we have found U. Okay, so that is the radiation intensity. Okay, so the radiation intensity is the angle, the power radiated through a unit solid angle. Okay, so you can find it like this. And also you have defined another one, nominalized radiation intensity. That is nothing but the radiation intensity is divided by the maximum radiation intensity. And we use this to draw the radiation pattern. Okay, this to draw the radiation pattern. And also you have defined U naught, that is the radiation intensity if that antenna is uniformly propagating all the direction. Okay, so that is the definition. Okay, this is the radiation intensity, radiation intensity, if that antenna is propagating or radiating, antenna is radiating uniformly in all direction, as a isotropic radiation, as a isotropic radiator. Okay, so that is that is defined by PT divided by 4-5. Okay, so these terms you should understand. Okay, so you know the importance of this one and this one. Okay, but this one also important. Okay, we will see it. Okay, okay, so that is it. Okay, and okay, now there is another term. Okay, that is called directivity. Okay, the other things. Okay, and other things. Okay, so you can see that this U. Okay, so you can see that this U in this case, okay, in the case of infinitely small dipole, this U is depending on theta. Okay, in other words, U is a function of theta for an infinitely small dipole. Okay, but sometimes this u also can be depend on the phi direction also. Okay, so normally this u, okay, the radiation intensity is a function of theta and phi. Okay, so this is normally a function of theta and phi. Okay, okay, in this case it is a function of only theta, it is not depending on the phi in the case of infinite small dipole. But the other antenna, okay, this u can be a variable of phi or variable of theta or variable of both. Okay, so that understanding we should have. Okay, so sometime radiation intensity is given as u theta phi. Okay, so that is means this u can be depend on theta and phi. Okay, okay, okay. Now there is another parameter. Okay, that is called the directivity. Okay, that is called the directivity. Okay, that is called directivity. And before the directivity, we defined another one that is called directivity function. Okay, directivity function. Okay, directivity function. Okay, so directivity function is also a function of theta and phi. Okay, so actually it is defined as u, the radiation intensity, that is theta and phi function. It is divided by u naught. Okay, so this is the uh, isotopic radiator power, radiation power, like isotropic like radiated intensity. Okay, so the directivity function is defined like this. Okay, so u naught is nothing but pt divided by 4 5. Okay, and I think you can find the directivity function using this one also. It is the radiation intensity is divided by pt divided by 4 5. That means 4 5 u theta phi divided by pt. Okay, 4 5 times the radiation intensity, that is a function of theta and phi, and divided by total power. Okay, so this is defined as directivity function. Okay, this is defined as directivity function. Okay, actually this is nothing but this is actually a measurement. Okay, this is actually the measurement of how the antenna is radiating efficiently in a certain direction. Okay, so using this directivity function, okay, you can measure the efficiency of the antenna, the radiating efficiency of antenna in a particular direction. Okay, so that is the use of the directivity function. Okay, and using this directivity function, okay, so I think now if I ask you to find the directivity function for the infinitely small antenna, maybe you can find this. Okay, if I ask you to find it infinitely small antenna, you can find this. Okay, because you know you have found the uh, radiation intensity. Okay, and you have found the total power also, then you can find the directivity function. Okay, so the directivity function for an infinitely small antenna will be 3 by 2 sine square theta. Okay, 3 by 2 sine square theta. Okay, so try to get this answer. It is very easy. you have to do the division. You have to do a division. Okay. So using the division, try to find this one. Okay. And you can see that the directivity function is a function of theta only. In this case, okay, it is not depending on the phi. Okay, it is only a function of theta. Okay, but for some antenna, it can be a function of phi or it can be a function of both theta and phi. Okay, so this is the directivity function of the infinite small antenna, infinite small dipole. Try to find this by yourself. Okay, and also defining we are defining another parameter. Okay, that is directivity. Okay, so directivity is the nothing but maximum of the directivity function, maximum of the directivity function. Okay, so that is the directivity. Okay, and it is defined as d for phi. Okay, so the d theta phi maximize when the, okay, so it is defined as 4 phi u theta phi u pt. Okay, so this is maximized when this u is maximized. Okay, because pt is a constant. No, it is the total radiated power that is a constant, and 4 phi u also a constant. Okay, but u is not constant. It is depending on theta and phi. Okay, it is depending on theta and phi. So the directivity function get its maximum value when the u theta phi is maximized. Okay, so that is the u max, no, 4 phi divided by u max, and it is divided by pt. You will get the directivity. Okay, directivity. Okay, so actually directivity is in the maximum direction. No? It is in maximum radiating direction. This is in maximum radiating direction. Radiating direction. I think you can understand it. Direction. Okay, maximum radiating direction. Okay. Okay. So if I ask you to find the max directivity of an infinitely small antenna, directivity of an infinitely small antenna, you can find it. Okay, you can find it using this one. Okay, so you have the function and the maximum directivity you will get when sine square theta is maximized. That is, the theta is equal to 5. Okay, 5 by 2. Okay, that is nothing but 3 divided by 2. Okay, so this is the directivity for a infinitely small length. Okay. Mm, mm, uh, Actually, this d has another explanation. So you can define this d like, so you can define, so you can explain like this. Okay. I think you can understand. Okay. If an antenna, okay, if an antenna has a d directivity, directivity, okay, that means, okay, that means, it means that, okay, it means that the maximum radiation intensity, radiation intensity, radiation intensity, intensity This is the maximum radiation intensity. Okay. Uh, that is d times d times d times of an isotopic radiate. Isotopic radiate. Topic radiate. Okay. So the directivity means that is the maximum radiation intensity uh, that is d times of an radiation isotopic radiate. Okay. So uh, so you can see that so if I explain it further, okay, infinite small antenna, you have 3 by 2 directivity. Okay, 3 by 2 directivity, that means 1.5 directivity, no? Okay. So we can say that radiation intensity of the broadside direction of this antenna is, because the infinitesimal antenna has the maximum radiation intensity in the broadside direction, no? Broadside direction. Okay. So that is the maximum radiation intensity direction. Okay. Direction of this antenna is 1.5 times than the isotopic radiator. Okay. Isotopic radiator that carry the same power. Okay. Okay, so that if you have that idea, that will be enough. Okay. And also sometimes this directivity d also uh, also given in dB. Okay, dB. Okay, because this is a ratio. Okay, it is a ratio 3 by 2 here. Okay, so you can you can you can uh, represent it in dB. Okay, you can convert it to dB. So what you have to do is that you have to take the 10 log 10 of the d value. Okay, so you will get the dB value. Okay, so sometimes directivity is given by dB also. Okay. Uh, and there is another very important parameter. Okay, there is another very important parameter that is called half power beam. Okay, that is called half power beam width. That is called half power beam width. Okay, half power beam width. Beam width. Half power beam width. That is, in short form, we tell it HPBW. Half power beam width. Okay. Actually, that is the angle between two half power points. Okay, that is the angle between two half power point. Okay, half power point in the radiation intensity pattern. Okay, in the radiation intensity pattern. Radiation intensity pattern. Okay, actually radiation intensity pattern is this. Okay, this is the radiation pattern, intensity pattern for an infinitely small antenna. Okay. Uh, so we normally used this normalized intensity or radiation intensity to draw the radiation pattern. Okay, so this is called the radiation pattern. Okay, so if you consider radiation pattern, okay, and if you get two half power point, okay, then that is the half power beam width. Okay. Okay, so we can consider the um, we can consider the infinitely small antenna. Okay, so this is the Z and this is Y. Okay, so our radiation intensity is like this. Okay, radiation intensity pattern is like this. Okay, so uh, so you can use the nominalized power. Okay, so this is the maximum power. No, this is the maximum power. Okay, and if it is nominalized, this is one. No, the maximum power is one. Okay, because U is defined as UN is defined as U divided by U max. Okay, U divided by U max. Okay, so the maximum power of the nominalized intensity will be one. Okay, so here the maximum power one. Okay, and half power is in this point maybe. Okay, half power. This is the half watt. So if you consider this is 1 watt, this will be the half watt. Okay, okay, and this is the 2 point half power point. Okay, and if you get the angle between this point and this point, okay, and if you consider this angle, that is the half power beam width. Okay, so what is the half power beam width of the uh, infinitely small antenna? What is the half power beam width of a infinite small antenna? What is? So you can see that here you should have half power, no? Okay. So you know that for a isotope infinitely small antenna, nominalized intensity is nothing but sin square theta. Okay. So at which theta it will take the half. Okay, so theta is measuring in this direction, no? Okay, theta is measuring in this direction. So for what theta, this un is half. Okay, this un is half. So you have to find sin square theta is equal to half. Okay, that is the half power, no? So sin theta is equal to 1 by root 2, and you can get the sine inverse of 1 by root 2, and you can find the theta value. Okay, find the theta value using a calculator. Okay, so if you calculate that one, let's calculate it. So if you calculate it, so you have to find the sine inverse. No? You have to find sine so, sine inverse. No? You have to find inverse sine. So you have to find in radians. For the sine radians. Okay. Sine inverse 1 divided by root 2. Okay, 45 degree, no? 45, it is in degree, no? This should be in degree, no? Okay, yeah, maybe this should be in degree. 45 degree, no? Yeah, it should not be a radians value, it should be a degree, no? Yeah, maybe 45. Okay, please check it. Okay, so sine here, the theta is nothing but 45. Okay, the theta is 45. Actually, this is the 45. Okay, this value is 45. Okay, and if you need to find this one. Okay, this is the half power beam. Okay, so you have to find this value alpha. Okay, so what is that? 90 minus 45. That is, you have again 45, and the half power beam with this 2 times of the alpha. No? So the HPW is nothing but HPBW for infinitely small antenna is nothing but 2 by 45, that is 90. Okay, please check it. Okay, I can't remember actually. Okay, so this should be the answer. Okay, and okay, so that is the half power beam width. Okay, and maybe another parameter is there, that is the antenna. It is called that antenna radiation resistance. Okay, radiation resistance. Radiation resistance. Okay, resistance. Okay, and it is defined as resistance. Okay, it is defined as, not defined. Okay, maybe explained as resistance which can be which can be which can dissipate the same power as the antenna carry the same current. Okay, same current. Okay, so the same power, that means the total power. Okay, same power means is the total power. Dissipate the total power when the antenna is carrying a current. Okay, antenna is current can be a, when the antenna is carrying a current. Okay, if the current is flowing through the antenna, and if it is dissipating the total power. Okay, total power is the PT. Okay, so that is called the radiation resistance. Okay, and it is defined as half. This is the current, and you have to get the square of the current. Okay, and divided by R radiation. Okay, so this is how the radiation resistance is defined. Okay, so if the antenna is carrying the current, through the antenna. Okay, if you consider a antenna. Okay, if you consider a resistance. Okay, and the resistance, if a current flowing through a resistor. Okay, and it dissipate the same power, same total power. Okay, the antenna that dissipated by the antenna, that radiated by the antenna. Okay, so that is called the radiation resistance. Okay, and this radiation resistance can be defined in 2 ways. Okay, that is depending on the current. Okay, depending on the current. Okay, so the sometime you are considering the maximum current. Okay, so I told you that antenna have several current distribution. No? Several current distributions. Okay, the current distribution may be changed. Okay, so it has a maximum current. Okay, and maybe, so if you consider the maximum current. Okay, maximum current, this I square, you have to consider the maximum current, the magnitude of the maximum current. In that way you can find the radiance resistance, and also you can find the radiation resistance related with the feed point current. Feed point current. Okay, feed point current. Okay. For example, okay, if you have a dipole like this, okay, and this is the feed point, okay, okay. So you can consider this point current, okay. So that is the Z. So if you place this along the Z axis as say, okay, the Z is equal to 0, you have a current, okay. You have a current, and if you consider that current and calculate the radiation resistance, that is the radiation resistance related to feed point current, okay. And in some point, maybe it has the maximum current, okay, maximum current. Maybe is a dash or something, okay. And if you consider this maximum current, and if you calculate the resistance radiance, that is the radiation resistance related with the maximum current, okay. So you can define two radiation resistance that is related with the maximum current and feed point current, okay. In some cases, maximum current may be the feed point current, because if the maximum current is the uh, feed point current, okay, it has only one radiation resistance, okay. So for an isotropic antenna, you know that I is uniform, okay. So the maximum current and feed point currents are same, okay. So you have only one radiation resistance for isotropic antenna, okay. Anyway, we don't know the current distribution, okay. We don't still we don't know the value for current, but we know that current is uniform, okay. So if you are given a current, this is the current flowing through the antenna, and if you have given the total power, you can find the radiation resistance, okay. Okay, so I think for our course, this discussion will be enough, okay. So basically we have considered some parameters, that is the uh, first we have found the magnetic vector potential, then we have found the H field and E field, okay. Then we have found some parameters, okay. So that is the average power density, S average, okay. So we have found these parameters, okay, S average, okay. And we have found the total radiated power, okay. Then we have found the uh, radiation intensity, okay. Radiation intensity, that is the uh, average power through a unit solid angle, okay. And we have found we have found we here we are defined three type of radiation resistance, radiation intensity, that is the nominalized radiation intensity, you divided by your max, okay. And u naught, okay, the same power that is dissipated through isotropic antenna, and also u, okay, the radiation intensity, okay. So that is the function of theta and phi, okay. So we have defined this one, okay. And after that we have find the directivity function, that is the theta and phi. Then we have found the directivity, okay, that is the maximum of the directivity function, okay. And then we have found the half power beam width and radiation resistance, okay. So these parameters we have found, okay. And these are general for anyone. These definitions are applicable for any type of antenna, okay. And we have calculate the value related with the infinitely small antenna, okay. And if you have time, okay, so do this after the exam, okay. For the exam you will not come that one, okay. So if you can try to find these things, okay. And also we have found the radiation pattern also. Once we have found the u, and we have found the radiation pattern also, radiation pattern, That is also a important factor. Okay. So basically we have found 1, 2, 3, 4, 5, 6, 7, 8. 8 parameters and H field and E field. Okay. Altogether 10. Okay. And also the magnetic vector potential. Okay. So these things we have found. Okay. So if I ask you to find these parameters for a small dipole, okay, for a small dipole, okay. So that is means small dipole means the dipole length should be less than lambda by 10, okay, and should be greater than lambda by 15, okay. So this is the small dipole, okay. And for the small dipole, okay, if you have a small dipole, this is like this, okay, like this, okay. And if you place is it in a z direction, in the same way we have done for a for the infinitely small antenna. So this is z and this is y, okay. And we have placed is like this, okay. And the current distribution is along the z axis, okay. So if you consider any point, z dash point, okay. So the current distribution is, okay, the current distribution is, it is in the z direction, okay. I 1 by 2 z dash, okay. So this is when the z dash in plus direction, this direction, okay. So that means z dash in that point is between 0 and you have symmetrically placed it all through the y-axis. So this part is L by 2 and this part is L by 2, okay. So this is L by 2, okay. And if the z dash is minus value, that means in this place, that means z should be less than minus L by 2 and greater than 0, okay. So at that time, it is also z direction, I 1 plus 2L by z dash, okay. So the current distribution is changed, okay. And it is, you have two current distribution for this one and this one, okay. So if you are given this current distribution, okay, maybe you can calculate, you should be able to calculate all these parameters, these 8 parameters. And also before that, you have to calculate magnetic vector potential, H field and E field. Then you can calculate the average power density, total power, uh, power radiation intensity, then the directivity function, okay, then the directivity, then the radiation pattern, then the half power beam width, then the radiation resistance, okay. All these parameters you should be able to calculate, okay. So only thing is you have to do the integral in different way, no. So this is the integral maybe difference, okay. But this one also not much complex, okay. Maybe you can try by yourself, okay. But don't do this just now. After the exam, you can do this, okay. And if you need to know, you can ask me, okay. After the exam, okay. No need to do this just now, okay. So after the exam, try to do this one, okay. And also, okay. And also, and there is another dipole that is called finite length dipole, okay. That is called finite length dipole, okay. Finite length dipole, okay. So that is the L should be greater than lambda by 8, lambda by 10. Okay. So if you consider, so I think we have talked and we have done some practicals using uh, half wave dipole, half wave dipole. Okay, so that half wave dipole is belongs to this category, finite length category, and for half wave dipole, L is equal to lambda by 2. Okay, L is equal to lambda by 2. Okay, that is the half wave dipole. L is equal to lambda by 2. Okay, and uh, but that current distribution somewhat complex actually. Okay, that current distribution is somewhat complex because it also may be that integration may be difficult. Okay, but you can try it. Okay, if you have time, you can try it. The current distribution for this uh, finite length dipole, okay, is like this. Okay, is like this. Okay, is like this. It is also in Z direction. If you place in symmetrically in Z, it is sine k L by 2 minus Z dash and Z naught I sine k L by 2 plus Z dash. Okay, and this is for Z dash is between 0 and L by 2 plus side. Okay, this is Z dash is minus L by 2 plus L by 2 due to 0. This is equal and this is equal. Okay, and this is for minus side. Okay, so maybe this integration may be difficult. Okay, but try to do it by yourself. Okay, maybe you can do it. Okay, so if you want to know this further, okay, you can ask me, then I will explain how we can calculate the parameters related with these dipoles also. Okay. Uh, so okay, so don't do this before the exam, okay? And I will do one tutorial uh, very soon, okay? So at that time I will discuss uh, some question, exam type questions, okay? One or two questions. So these are exactly exam type question, okay? So you can refer them, okay? Okay, thank you.